So the problem is how can we find out the beta 0 and the beta 1, right? So we will introduce this ordinary least square method. So last week we go over the least square method, but here we're trying to find out beta 0 and beta 1 so that we can minimize the square error. So what is the square error here? Is we will have an observation, n number of observation, x1, x1, y1. This is first observation. This should be the paired observation, paired data, x1, y1, x2, y2, x3, y3, and so on. Okay, and then we will draw a line. Okay, as you can see, this is x-axis and this is y-axis. So I want to draw a line. So this is the, as you can see, this is a linear line, and then error is the difference between this line and then the real data. So this is the error. This is the error, right? And this is the error. All of this is here you can see this residual, but so this case, this is the you can see the one, some part is minus, some part is positive. Of course, the expectation should be right. So given x, what is the my estimation? This is my estimation because this line is my estimation by this model, linear model, and then this is the actual y, the real y. So if you calculate the difference, okay, and then I want to minimize this difference, total difference. So here, as you can see, regression residual is the real y minus estimated y. Here the y is the from real data. This is from real data. This is what? This is by linear model. Right? That's why you can replace a y hat into this one. Right? So this is like yi minus, which is the beta 0 minus beta 1 x I here plus. Okay, that's why we have a hat is because the real beta, here the beta 0 and beta 1 is the population regression coefficient. But since we are using data, sample data, so I'm estimating beta 0 and then estimating beta 1 here. So that's why we have a hat. And y is also estimated of the y. And then we trying to minimize the total error. Here, why we take a square is because since we have a positive error and negative error, and as you know, the expectation of the error should be 0, which means we have a same amount of positive error and same amount of negative error. So if we mix up together, yeah, you will have a 0, even though doesn't matter you have a pretty bad model or good model, summation will be 0. So what you can expect, is that if you calculate the summation of the u hat, right, I equals 1 to n, this should be 0. Is this because expected value of u should be 0, right? You know what is the expectation? Is you just like calculating the average. So if you add up all u divided by n, this should be 0, which means this n cannot be 0, so this should be 0. That's why we wanna have a plus and minus cancel out each other, just like when we do the variance. That's why we apply the square so that everything becomes positive, and then we add up, and I want to minimize its total error. That's a least square, ordinary least square estimator. Okay, so using that, trying to minimize this one, so you can using this form, and then actually you have to take a derivative regarding to the beta 1 and beta 0, then you will get what should be the optimal solution. So this will be the beta 1 estimate, and this will be the beta 0 estimate. This is actually from the equation directly. Y I should be the beta 0 minus beta. Right? So if you just move y beta 0 and then everything move, right? So this, yeah, this should be plus. So if you subtract both sides, what you can get is y I, but this is all different cases, right? So you can just simply take an average of it. You can take an average of it, and then you can find out this is a beta 0. But you have to know what is the estimate beta 1 here, so this should be going there. Least square estimator. So this is a little different way, but we will define this sum of square. So x minus x bar square, which is, if you divide by n, this is similar to the variance, right? But this is not exactly the variance. So you can just simply calculate this summation of the difference square. Okay, this is a summation of square for y. And since this is square, instead of using x square or y square, you can calculate as sum of square xy. So it's one part x and one part y. This is similar to the actually the correlation coefficient. This is not exactly correlation coefficient. Okay, so just like this is not exactly the variance, right? So this is related to correlation coefficient, but not exactly. And then regression estimator is just like x and y divided by x. Okay, and then this is the same from the previous one, but if we take a look at it here, this is about the x, right? And this is about x and y together. Standard error of the estimator. So later we will use these things. That's why the variance of population regression error will have this one. So we don't know. An unbiased estimator of the variance of error should be calculated in this way. This is about calculating the error and square, and we divide n minus 2. Why we divide by n minus 2? So usually for the regular variance, right, formula, we unbiased sample variance, we divide by n minus 1, right? Do you remember? This is a sample, we take n minus 1. However, we have to take n minus 2 here, because in error we contain here what we in this formula, what kind of parameter estimator we have. We use this one, right? X bar is the estimator of our mean, mu, right? So mu is a parameter mean, a population mean, and x bar is a sample mean. So we use the data and we estimate the one parameter, which is our mean. So we use the one parameter. That's why you take it out to the one here. Actually, this is a degree of freedom. Since we use a one estimator here, that's why we subtract 1 here. Degree of freedom reduced by 1. The reason is like about mean. Let's say I have three numbers. What I can tell is the mean is 3. So I can use a lot of different number. I can use a 1 or 2. However, the 2 make a mean 3. So here I have to have a 6. 6 is not your freedom. I can put 1 and 2, right? I can put like a 5, 2. However, my last number to make mean 3, I cannot choose any number here. Here I can put any number here. Second number I can put any number here, but third number should be calculated by mean. That's why I don't have a freedom to put any number here. So how many number I can put for free, I mean freely I can choose any number. It's a 2 number. Even though n number of sample is 3, since we have a mean here, I have only 2 number for free, and the third number will be decided by the number of mean. So this is the what we can get some idea of the degree of freedom. So since we use only we estimate one variable here, that's why we take around 1. However, if you take a look at this y hat, we use two estimator, two variable estimator, right? We estimate this and we estimate this too. So we use a two variable, two parameter estimate. That's why you subtract 2. Again, this is the degree of freedom. That's why it's a n-2 instead of n-1. Okay, standard error is s divided by square root of SSX. SSX is what we already seen. That's the sigma of x I minus x bar square. Okay,